Hi there, good evening, good afternoon, good morning, whatever your current situation happens to be. Let me get into presentation mode here. Welcome to my own personal systems engineering capstone tips, pointers, rules of thumbs, common mistakes, etc. This particular presentation is not kind of a review of the systems engineering project guidelines and requirements. You have to take it upon yourself to review these guidelines and requirements. And once again, the area that you can find them is, let me go into the Capstone website here. These are very critical, by the way. So if you go, it's in my organizations right here, 645-800. So click on that. Over here, course guidelines, you'll click that. And here we go. So project overview and guidelines. This overview is a presentation that Christian Utera or one of the other instructors already gave you, and I'm not going to go through that again with you. And the guidelines are right here. That's what I have pulled up on this PDF. These are just my own personal kind of pointers, common things that I give students feedback on as I grade their submissions. Areas of focus, I think most of the students should focus on and whatnot. So it's meant more as an informal kind of steering method than it is a formal presentation on the project. So with that, it's only 20-something slides, so let's go ahead and go on through. Here's the sequence of events for the project. Most students follow this sequence of events where you're going to get your concept approved, and then you'll generate your proposal, then you'll generate your requirements analysis report after that, and then your functional analysis report. And then you might do a trade study to down select an alternative for a subsystem or component. And then your system concept design report would be updated. You generate your test report after that, and then you'll come up with your A spec, and then you'll generate your risk report, and then you'll have your final report and presentation. I think that's all of them. All right, let's just a couple holistic things, big picture things to think about as you work your way through the project. You have to think about constantly as you're going through this project that honestly, it's not about the architecture that you developed. Don't let that be the primary focus. The purpose of all of this is to prove to the university that you have systems engineering mastered. The purpose is not to develop a complete system architecture for a widget, all right? Knowing that, understand that the architecture itself is the means by which that you demonstrate mastery over systems engineering. So that's how we know that you have the subject matter mastered or not, as we take a look at your architecture and your explanation and defense of that architecture when you give your oral out brief. One of the areas of focus you should have at all times is the rubric found at the back of the guidelines. And a lot of students ignore this, but I always emphasize to my students, and I know this is tiny and it's like, what the heck is that thing? But this is the rubric. And what you've got is you've got the column, the dark column over here on the right. These are each of your artifacts, right? So you've got the criteria, understanding of core principles, defense of the project. This form is exactly what I use to grade your deliverables and exactly what CJ uses or whoever you're out briefing to, be it Dr. Flanagan or whoever, what they're going to use to assess the success of your project. So effective leadership, here's the actual artifacts. There's the concept and proposal. Those are all the same documents, the proposal, the requirements analysis report, functional analysis report, concept design report, and then it's continued down here on this page, trade study, etc., system spec, that's the A spec, T&E plan, risk management, final report and presentation, etc., right? And I want you to focus this whole time on this proficient column right here. Notice that it's 86 to 100, so it doesn't guarantee you an A, and I can't guarantee you an A either. It really depends, if you do a great job on your architecture, but you do a bad job defending your architecture and, showing good leadership and having a clear understanding of the core SE principles, then you might get, a B or something, or a low B, or maybe a C. That's very rare. In fact, I would say if you are under my tutelage, you're almost guaranteed an A. Not always. Most of my students get an A. And some of them get a B just because of the things I just talked about. All right. So if I am your mentor, then there's a very high likelihood that you're going to get an A if you follow this proficient column right here. So go through each of the artifacts, read the proficient column, and make sure that each of your deliverables meets these standards right here, right? And they're pretty subjective. Let's pick a random one. I'm going to pick, I don't know, something over here. Let's pick the no, let's pick the functional analysis report. It says right here, sorry about all the zooming. Functional analysis is thorough. Decomposition is appropriate for the project. It's a bit subjective, right? Architecture is well thought out and demonstrates tight binding and loose coupling. Traceability of functions to the requirements is complete, and the gaps are properly addressed. If your functional architecture meets those standards, then you're probably going to do pretty well on it, right? So focus on the rubric. That's what the rubric is. The 3 textbooks that I always recommend my students use are the Dr. Kozikoff Systems Engineering textbook. You either have the 2nd or the 3rd edition. 3rd edition just came out in 2020. If you don't have it, no big deal. The 2nd edition is fine as well. So Kozikoff, 2nd or 3rd edition. Charles Wasson, the Systems Engineering Analysis, Design and Development, I think it's called. It's the 2nd edition, which is printed in 2015. So check that out. In fact, I have this kind of preloaded on my my Adobe here. I get out of my search, close out of the search, and let's see if it's on my quick list. All right, Adobe, it is not being friendly to me. Here it is. So this is what the front cover looks like. Charles Wasson, System Engineering Analysis, Design and Development. So I was right. Awesome. The area of this book that I really want to emphasize is part 1. So let's see here. Part 1, Systems Engineering Analysis Concepts. All right, part 1, and in particular, I want you to focus a lot on chapter 3, 4, all the way through part 1, all of it. Levels of abstraction, framework, modeling the mission is big, analytical problem solving. So all of that, right? And the rest of this is covered by Kazi, etc. The one thing that this book has that's better than the other books is part 1 of it, is the development of the mission domain is what it's called. None of the other textbooks have such a robust explanation of how to develop the mission domain than this one. All right, so check this one out for that. And I'll mention it in my presentation as I carry through. Dennis Beatty is the next textbook. It's a bit drier than the other ones. You probably already know that at this point. But there's really the requirements analysis chapter in that book is really good. So take a second look at the requirements analysis chapter in that book. In particular, he talks about how to quantify or how to provide measures of performance to requirements that are very difficult or that are subjective, like your human factors related requirements, the look feel kind of requirements or aesthetic kind of requirements. And he's got a method in there that he talks about for how to bound or make testable, if you will, those kinds of requirements. So check that out. And Kozikoff is kind of a blanket book. Everything in that book is applicable, right? Next slide, to use an MBSE tool or not to use an MBSE tool, the one thing that I will mention is that almost all of my students, like 99% of them, I've had over 100 students that I've brought through the program since I've been a mentor, and almost all of them, 95 plus of them, have all said that they wish they use MBSE tool, and that they said they wish they did if they did not, and that they are glad they did if they did, all right? So don't think of it as a burden. Think of it as a tool that will save you a lot of time in the end. So I highly recommend using an MBSE tool. It significantly reduces workload, especially if you need to make changes to your architecture. Recommendations are the standard ones. You've probably seen all of these offered to you throughout your different courses. The first one that I will recommend is Vitec Core. It's the easiest one to use. And I've got my my lecture, not my lecture, my tutorials on YouTube on how to use that. And if you need to know where those are, we can go to, let's see here. Let's go to YouTube. And all we're going to do when we go in here is type in JHU Olson like this. And there it is. The real irony of this is since I created this page, YouTube's got some new terms and conditions and they've locked me out of this and I can't get in. They want a phone number to get in, but my phone number is tied to my personal YouTube account. So I can't get in here and update any of the videos, but they're just as applicable. Go to the playlists. There's my using Vitech Core playlist, 13 videos. And then I've also got a little project walkthrough that I started in there as well. So check those out. JHU Olson is what it is, right? Back to this. So Core, I recommend the No Magic and the Sparks enterprise architecture tools. I only recommend those if you are a system modeler in your professional life, or you plan on becoming a system modeler as a profession. The reason why is both of those tools have a rather steep learning curve. No Magic has a steeper learning curve, I think, than Sparks does. Both are great tools. I use Sparks EA more than the other one, just because I have the full unlocked version, whereas the No Magic one has a limited amount of, the academic version has a limited amount of entities that you can use. Both have a steep learning curve, like I said, and they both require familiarity with UML and SysML. So if you're going to get into that, or if you already are into that in your professional life, then use probably No Magic or Sparks. You have to pay money out of your own pocket for Sparks. The EDU license, I think it's like $170 as of the making of this video. That's what it cost me as an instructor. I think students have the same price, but it's the full unlocked version. I think it's got a splash page or the top of each of your deliverables or something. It says that this is the education version, which is no big deal to me, right? So that's my recommendation there. There's Innoslate. I usually don't recommend Innoslate just because it's unstable. It runs off Flash, and as you know, Flash is going away. Unless they've converted it to HTML5, they might have since I've checked it out, but it was pretty unstable the last time I used it. So it is a great tool when it works. Very easy, keeps everything online. So all you have to do is sign in, have internet connection, and you can sign in and use it. All right, to download any of those, just a reminder, you're going to go to your main Blackboard page here, where you've got all your courses and everything. And once again, in my organizations, remember I showed you there's the Capstone. Well, in this same area, you've got JHU SE Tool Community, right? So click on that, should have access to that. And then over here on the left is Systems Engineering Tools, click on that. And then here you go. Just click whichever tool you want to use, and then the instructions are found inside of here, right? And these are, the keys are renewed every semester and whatnot, right? To continue, concept ideas, let's talk about those. To choose a concept, on top of what's talked about in the guidelines talks a little bit about choosing a concept. Once again, this presentation is above the guidelines. This is above and beyond the guidelines. This is just what I recommend for my students. So choose a concept that can't be copied and pasted from existing designs, right? So that's kind of obvious. You don't want to plagiarize, even engineering designs, you don't want to plagiarize those. Something that fascinates you, if it's a dull subject or a subject that you really don't know much at all about, then you're going to be challenged to get through the capstone. Choose a concept that's not too difficult. So self-driving cars, probably too difficult. Launch vehicle, satellite, aircraft. Those are obviously, those take huge teams to develop the concept for those. So don't choose something that complex. Also, don't choose something that's too simple. So home appliances, applications for smartphones, etc., exercise equipment. Those are too simple, and you can't get back to the main point here. You can't prove mastery of systems engineering if your concept is too simple. It's got to have a healthy mixture of hardware and software as well, right? Things that are off limits for the concepts is a software intensive system. This is a master's degree in systems engineering. It's not a master's degree in computer science or computer engineering, right? So software intensive systems are off limits. It can't be a software architecture that's UML or whatever. It's got to be the full, a healthy mixture, like I said, of hardware and software, right? Most students lean towards the hardware side, so keep that in mind too. It cannot be database centric, so don't think about creating some kind of a huge database where everybody puts in their data and um, provide a repository and stuff. That's so normal that it's not worth systems engineering, right? Off limits also is the integration of off-the-shelf elements or consumer off-the-shelf elements. Those are called COTS, obviously, and federated elements. So it's more than just purchasing stuff off of a shelf and integrating it together to make it into a bigger system as a whole. In other words, you've got to have some elements that beg for development, that beg for you to give a developer a specification and have them develop a system based on the words in that specification, right? So it's more than the integration of COTS and federated elements. Also, it's not IT centric. So don't think about coming up with this big IT infrastructure, a workplace repository of all of your IT needs or whatever. That's once again so common that it does not need systems engineering. Not that it's not so common. It's also, I don't want to say it's not simple stuff, but it's stuff that's been done so often that there's already a pre-established kind of set of architectures for that, and it doesn't beg for systems engineering, IT-centric systems. Obviously classified, you don't want to be leaking classified information. So if you're doing something that's work-related, stay out of the classified domain. Also, if it's FOUO, if you're a government employee and it's FOUO, we can sign an NDA with you as well as proprietary. So Johns Hopkins can sign an NDA if it's either FOUO or proprietary, right? So keep those two things in mind. Usually students kind of stay out of their work domain, but some students do. Some students are paid to go through the program specifically so that they can create an architecture for something for work. That's happened a couple times in the past. So in those cases, the university will sign an NDA, right? Once you have a good concept, run it by your mentor. That would be me via email. It's a pretty informal process here in the beginning. Once it's approved by your mentor, repeat the same process for the instructor. So I'll provide you recommendations or feedback or whatever. You make corrections. It's just a paragraph that explains what your system is, the kinds of things that it could be composed of and whatnot. Just an explanation of how it might work. And then after it's approved by probably CJ or Dave Flanagan, then you have permission to proceed to developing your actual proposal. Before we proceed, I just threw this in here to kind of give you an idea of what the project looks like in terms of the life cycle. So recall from your COSI textbook that you've got 3 stages. One's the concept development stage. The next is the engineering development stage, and the third is the post-development stage. It's right on the front cover of your COSI textbook. And this capstone project is only the concept development stage, but also recall that there's 3 phases inside of the concept development stage. There's needs analysis, there's concept exploration, and there's concept definition. You'll do all 3 of those phases as a part of your capstone project. So when you start to get into the proposal and generate the proposal, and you're looking for how to start, what to do, where to go, well, turn to the textbook and read needs analysis chapter, because you have to do needs analysis, and the output out of that is your proposal, right? So also recall that these right here, these are your systems engineering activities. You've got requirements analysis, functional definition, physical definition, and then design validation is what COSI calls it, right? And it's the same for every one of these phases. They go by slightly different names and have slightly different activities that occur inside of them, and your COSI textbook runs you through the details of those. So take a look at those. Once your proposal is approved, then you'll start to do concept exploration, right? This implies that you're going to have some of each of the elements from each of the domains, meaning that you're going to have, and if you use MBSE, you're going to start to populate your MBSE tool with some needs. Those will be in your requirements. You'll populate it with some rudimentary high-level functionality in the functional domain, and you might possibly create a skeleton architecture to get everything kind of up and running. If you've taken the MBSE course, they probably talk to you about setting up a skeleton architecture, and you probably want to set one of those up. One thing I do want to emphasize, and this is kind of optional for the capstone project, but Another thing that Wasson talks about in this textbook is, let me find it here. It is, there's your phases modes. Here it is. Chapter 9, the system of interest is what we're focusing on here. All right, take a look at figure 9.1. When you model your system, this is probably a pretty good skeleton to look at, right? So you've got the enterprise that your system is inside of. You've got higher order systems to be concerned with. These are what's on the outside of your context diagram, typically. You've got the user's level 0 system of interest. This is your system. In the real world, your system is composed of two primary elements. One of them is the mission system. That's the thing everybody cares about. That's the helicopter or the UAV or the car or whatever it happens to be, or multiple ones. And the other one is the enabling system elements, right? So these are your mission resources and all that stuff. So these two together are bound by the boundaries of your system, right? And you as an organization are responsible typically for everything inside those boundaries, as well as all of the arrows that are touching the boundaries of your system. So you're responsible for reacting to each of those elements, providing outputs to each of those if needed, etc. All right. So this might be a good place to start. And I say it's kind of optional because almost all the students skip the enabling systems and just use mission systems. But I allow you the option if you'd like to architect at least part of the enabling system, or at least put it in there as a placeholder, just so that we know that you understand that there are additional things other than just the mission system. And that's a big thing I really want you to walk away from the whole program understanding, is that when you bound your system, it's more than the widget, it's more than the thingy that you care about. It's also all of the enabling elements as well, because as a systems engineer slash project manager, you've got to scope out all of that stuff. You've got to come up with cost and schedule estimates and resource requirements and statements of work and all of that other stuff for all of it, not just the mission system, but all of it, right? And your statement of work will usually focus on the enabling system requirements, while the mission system is your A spec. So that's kind of a differentiation there. So figure 9.1 for that. All right. Once your requirements analysis report is generated, then we get into concept definition, where you're defining your concept, right? Out of the functional definition activity, you're going to get your functional analysis report. Out of the physical design, activity, you're going to get your trade study and your concept design report, because that reflects your physical domain. And then your design validation step right there, you'll validate the architecture, and then out comes the A spec, as well as the other, like your test plan and whatnot, for that. So keep that in mind. This will come up several times. Here it is again, in fact. So if you could see that, right? So the proposal itself, there's a template that's provided in the project guidelines for the proposal. So take a look at that. Use that template. If everything in your proposal is from the project guidelines, then you're good to go. You're golden. Other things is focus on capturing the need. When I see that need paragraph, I usually look for a sentence or something that says there's a need for a system that does X, Y, and Z. The reason for that is because this forms the apex of your requirements hierarchy. You're going to enter this statement into your requirements tool, and that will form the foundation or the apex of all of the requirements for your system, right? So that's the need statement. How do you write a need statement? Take a look at the intro course. I don't know which version of the intro course you've taken. There have been a couple of different versions, but both of them have the lesson, and the lesson's unchanged between the two versions. Just depends on which module it falls in. It's the requirements analysis module, and it's this is the intro course. It's one of the lessons in here. It is, uh-oh, did I mislead? No, it's problem definition. 3A, problem definition and need statement. So it's the very first one. This is the latest version of the course. This is summer of 2018 is when this was deployed. If you're working in an earlier version, I think module 4 was the requirements analysis, what's it called, module. You're going to want to generate a context diagram or more than one context diagram. Those are based on preliminary mission analysis. What I mean by that is don't just put it together just willy-nilly, okay? Think about the mission that the system's performing and who's talking to your system and who wants stuff out of your system. Those are the things that surround your system on the context diagram. Don't just make up, people and things to put on the context diagram because it's an exercise in academia or whatever. It's got to be based on just a run through in your own mind, in fact, of the preliminary mission. Think about a day in the life of the system. Not really a full 24-hour period, obviously, but just what does the system do throughout a day in the life of the system? Understand where you are also in the life cycle, and that I already showed you that here. Is by the time you're done with the proposal, you should have gone through each of the activities in the systems engineering activities up there, right? The system concept diagram that it asks for in the guidelines. Once again, go to the guidelines always. But the concept diagram, it's not written in stone, all right? So you might be tempted to use that concept diagram as a foundation for your physical domain. Don't do that, all right? Understand its purpose, and its purpose is just to prove feasibility, just to show myself and CJ or Dave Flanagan that your concept is sound and that it's feasible. After that, you can kind of forget that you created it because you're going to be approaching it from the top down, right? So you just kind of threw together some rudimentary ideas about how this thing could come together on a physical side, right, as a concept diagram. Don't get too detailed with it either. Just understand that it's very, very malleable and it's totally open to being changed, right? Once again, check the rubric. You're going to see that on every slide. So for the proposal, before you submit it, check the rubric, make sure that all of the elements in the rubric are covered by the proposal. Let's talk about the requirements analysis report. Focus on system level capabilities, right? So a lot of the time I'll get requirement reports with a lot of really tiny little detailed requirements inside of it, like 200 requirements. That is way too much detail, right? So I should see all the requirements should say the system shall and then do something, right? Each one, the system shall do something. You can be arbitrary with it too sometimes. The capabilities, for example, you'll do user interviews. That's one thing I forgot to do in here is your user interviews, but that's talked about in your guidelines. But you'll do potential user interviews, stakeholder interviews, and you'll get out of them capabilities that you want out of the system. Some of them might try and force solutions into the system, and you always want to avoid that, obviously. But they'll give you capabilities, and they might give them to you in a paragraph form, and you could directly translate those into requirements if you'd like. Some of them will be rather subjective, like they want the system to work in. They'll probably say something like all weather conditions or something like that. Understand in your mind what they mean when they say the words all weather conditions. Usually they don't mean all possible weather conditions. Like, do we want our UAV to fly in, you know, category 5 hurricane conditions? Probably not. But what they mean is if it's drizzly outside or, if there's slight wind or something like that. So it's important to understand what the user is really after and rewatch some of the videos throughout some of your courses, especially the concept development course about how to elicit requirements from users and stakeholders, right? And work through those to get some requirements out of that. Also, a lot of the requirements are based very heavily on a mission analysis. So make sure that your ConOps and use cases are very robust. And once again, I point to Charles Watson's section 1. Right? It's a lot to read. I'll give you that. It's a lot to read. But trust me, if you read section 1 in this textbook, part 1, I should say, let's see, it goes from page 50 all the way to page 255. That's a lot to read. But if you're doing systems engineering as a profession, it will pay dividends, exponential dividends, because nobody out there really does mission analysis or even knows how to do mission analysis. If you've got this stuff down right here, then you will be a master of your domain and you'll thank me for it. So check out section 1. And one thing I will say is, let me pull up like just an arbitrary chapter here. He's got some pretty complex stuff going on in here for a lot of this. Let me go to the other diagram. This is, believe it or not, the simpler version of of the uh, of the different comparisons here. The one I'm looking for is, I think it's in a pre, but he's got some pretty complicated. Don't let that discourage you. Just understand. And then there was one thing too that I just ran into, which is critical, and that is here it is. Nope, it's this chart here, where you're getting objectives. I call them, in this slide, I call them capabilities, but Wasson calls them objectives. They're the same thing. Where you've got operating environmental conditions, you get pre-mission phase. A lot of students forget about that. The mission phase, most people and most students focus only on the mission phase. And then you've got post-mission phase, and that's just for one mission. You might have multiple missions. And each one probably begs for a different context diagram too, by the way, right? So keep those in mind. Each one of these phases between different time periods, they can be chunked out. You want to decompose those into different things, into different time periods, and get from those different objectives that your system needs to perform, and then you'll just turn those into requirements. The system shall allow for preparing a pre-flight within a certain period of time, right? So that's how you come up with a lot of your requirements, is you perform mission analysis, all right? So check out Wasson, part 1 of the textbook. Let's see if there's any other glaring ones that I want to bring up. Like, don't get too discouraged by these kinds of things, but he's talking about how to get measures of performance from all of these different things, all these different capabilities, right? All these different capabilities right here that have been identified. You need to come up with measures of performance for each of those, and you'll do that either in this report or in your A-spec, right? Talk about use cases, and use cases are used to develop your functional domain primarily, because use cases are low level. Use cases are typically lower level, and your design engineers are going to use those to help design the system, but you can create them at the system level too. Some sequence diagrams. So already we've got kind of a arbitrary functional domain created here in this diagram, right? And he's allocated it to different subsystems in these swim lanes right here, right? So check that out. You'll be better for it. So the capabilities and requirements are based on mission analysis, your ConOps, use cases. Most students that submit the RAR, they just have probably, I don't know, 2 to 5 pages description of the ConOps. Tell the story of the system. That's all it really is. And it should be in the simplest terms that you can understand. Don't make it too complex. Create more than one scenario, create more than one mission if you need to, and walk through a day in the life of those missions, and then look at the mission and pull out capabilities that the system needs to perform and turn those capabilities into shall statements. And they're all system level in the requirements analysis report. I should not see requirements in there that say the display shall do something or the GPS needs to do whatever, right? And that gets to my next point. No solutions at all. I should not see any solutions in here unless I should say no solutions unless it's driven in there by some external entity like regulations. Like if you're doing a car, obviously you're going to have seatbelts and things like that. You won't see that in a capabilities or requirements analysis report, capabilities level document. You'll just say it shall be compliant with the most recent requirements in there instead. You want to tie your requirements to MOEs. Those are your measures of effectiveness. And that's really like the user's interpretation of how well they want the system to perform. They can be quantified, or they can also beg for analysis. Like they can be arbitrary, they can be subjective. For example, the system shall do X as well as or better than current systems. That's the MOE. The MOE is as well as or better than current systems. That's the subjective. It's a subjective MOE, but it's an MOE nevertheless. So it begs for analysis. It begs for you to figure out how fast or how well a current system does its thing. And then that will become your quantified requirement, your decomposed or derived requirement, right? So that would actually be a derived requirement from that. Um, Usually this document, the requirements analysis report, will have 50 to 75-ish requirements, sometimes more, sometimes less, depending on the kind of system that you're developing for your project. Don't forget about your key performance parameters. It's rare that students forget that, but some students forget your key performance parameters. Choose wisely. Don't choose too many. So these are the things that the system must, the capabilities that the system must have. If it doesn't have those, then it's not worth developing the system at all, right? That's what the KPPs are, right? So choose only a few. Even in the real world, for like major combat systems, jet fighters and helicopters and stuff, they will have usually less than 10 KPPs, and about half of those KPPs are mandated from the offices of the Secretary of Defense, right? Don't forget about your earned value management updates also, by the way. So you've got to do EVM for this project. And once again, check the rubric for your requirements analysis report. Common mistakes that I see in the requirements analysis report: poor mission domain. So it's not present at all, or it's not good enough to get requirements out of. So that leads me to ask, where'd you get all these requirements? I don't see them in your Q&A with your stakeholders and your user and stakeholder community. I don't see any of these things addressed. So where'd you pull them? Like, where'd you get all these requirements? That's the question I'll be asking if you have a poor mission domain description. Once again, see Olson part 1. Another common mistake is forcing solutions into the system. For example, saying that the system shall use GPS. Why? Why do you need to use GPS? Instead, ask why. So whatever the thing is that you're tempted to put in there that's physical, ask yourself why you want that in there. And the answer is usually the capability that you desire. So why GPS? Because you want to be able to provide location information. So that's the capability. The system shall provide location information, or the system shall be able to provide location information, something like that. All right. So we don't want to direct GPS. There's other solutions, believe it or not, out there other than GPS. That's a very specific example, but that's all right. Other things I see is not testable. There's no measures of performance. That means that there's no thresholds and objectives tied to those requirements. You want all the requirements to be testable to some degree, right? Even if it's subjective like this, this as well as or better than current systems, this begs for the system validator to figure that out if you don't answer it for them, all right? But it's still there. So you want things to be, all the requirements to be testable, and I always encourage students to use thresholds and objectives. I say always. Thresholds and objectives are based on mission analysis and the true need. All right, so don't just arbitrarily invent some numbers. It needs to be able to go from 0 to 60 in 5 seconds as a threshold and 3.5 seconds as an objective. Why? Why those numbers? Well, because the user wants it like that. In order to win the race car race or the drag race or whatever, it has to be that. Okay, that's justification. That's fine. But they're based on something. You just don't arbitrarily throw numbers in there, right? Another common mistake is arbitrary requirements. Things that you might have seen in other specifications out there in the real world or in class projects that you just throw into your spec just because you've seen them put in there before. I see this is true mostly with reliability related or ilities related requirements, especially reliability is probably the biggest culprit. So why reliability? This is a very detailed and fascinating subject matter, I think, reliability is, but why is the question I always ask. Why do you say that the mean time between failure is X? Where'd that come from, right? And that just tells me you don't understand how reliability works, how reliability requirements are derived, and they are come about. How would you say that? How you come about them. So understand how you come about those kinds of requirements in the first place. Usually you want to have a mission readiness capability requirement, and that mission readiness capability requirement, usually called A sub O, by the way, operational availability, and that's your typically the apex or the capstone of your reliability requirements. How do you make sure that the system is available for use 98% of the time? And what do you mean by time? As another question. Well, it needs to be up for this amount of time. It can only be down for that amount of time, etc. That takes a lot of analysis, which is deeper than the requirements analysis report. So I shouldn't see I guess the point of the reliability example is I shouldn't see detailed reliability requirements in the requirements analysis report unless they're driven in there by something external, right? Another common mistake is no traceability or poor traceability or no hierarchy for your requirements. You just have a giant list of requirements and they're all numbered level 2 or something, right? So that's the wrong way to go about it. Usually the first requirement in your list is your need statement, right? So 1.0 is the need statement, and then 1.1 is the few derived requirements from your need statement. So your need statement might be a tiny little, a bulletized list or a commatized list. It's got commas separating the different capabilities that are described by it, X, Y, and Z. Remember that? I put that a couple of slides ago, right here. There's a need for a system that does X, Y, and Z. Each one of those begs for a capability requirement. So system shall be capable of X, system shall be capable of Y, system shall be capable of Z. That's at level 2 underneath that, right? So that begins your hierarchy. And then you have to do analysis to figure out how well they need to perform those things, right? So once you start being tempted to go inside of the system and figure out how, the different kinds of subsystems and components, then you're going way too far, right? So probably down to level 3-ish is where you want to go. So at least level 3, probably at most level 3 for a lot of it, right? So that's where you want to be for how deep you go into the requirements analysis report. Capability level requirements for the whole entire system. I like to envision in my mind the system as just like a fuzzy cloud, and you don't know what it looks like or what it's composed of or anything. You just know that, like an ATM, you know that you tell it that you want money and it gives you the money. It's magic. This early in the life cycle, you don't know that it's got a screen and that it's got a keypad and that it's got an ATM card and all that it gives you a receipt and all of that stuff. You don't know all that stuff yet. You just know the capabilities. It's capable of authenticating the user. It's capable of communicating with your bank. It's capable of providing account ledger or tracking the account ledger or deducting your account by a certain amount, etc. Right? Those are the kinds of capabilities you look for from that. Another mistake is that it's too deep, that you go, deeper than level 3, which is rare. The system level capabilities only is what we want. Think if you're in the DoD or the government overall, think about your initial capabilities document, your ICD. Those are tiny, right? So for for the next fifth generation stealth jet fighter, we'll have an ICD that's 10 pages big, right? Also called a stakeholder requirements document for those that follow the IEEE 15288 standard. Wasson also calls it the stakeholder requirements document. Save the details for the A-spec. So the requirements analysis report lays the foundation, right? This lays the foundation. This is a result of you exploring your concepts. So once again, concept exploration is what you're performed, and you arrive at the requirements analysis report from that, okay? Let's get into the functional analysis report now. And once again, that is over here after you're starting to define the concept. Right here, you're analyzing the requirements from the requirements analysis report. So this flows right back up in here. You're analyzing those requirements. And now you have to come up with the story for how to meet those requirements in the form of your functional domain. And this is by far, the functional analysis report is by far the most difficult, time-consuming part of the entire project. Takes about 50 to 70 labor hours, sometimes more, sometimes less, depending. The question usually is, where do you start? Because it's so overwhelming and it's hard to think about where you'd start. Well, start with the context diagram. Model it. Model your context diagram. Look at the inputs and outputs going to and from your system. Let me try and find something real quick here. I'm going to try and find my context diagram. It's not going to be in the intro course. It's going to be in my other course. And I think it's in, this is going to be too hard for me to find it. It might be in, here we go, scripts, no. Here we go, infographic. This will work. Let's open this infographic. All right. Here is a context diagram for an ATM, and I just labeled it. Right, so you've got inputs and outputs, and all of these are your FEDSAM elements, forces, energy, data signals, and materials that go from outside elements to your system, right? Here's a list of them, right? Forces, energy, data signals, and materials are your focus for your context diagram. So keep that in mind. So you start with the context diagrams. You can model it in your architecture, create a function, the primary function that your system needs to perform as like the system, as the top level function, and create the system, the external entities. You don't have to create their functions, just create the entities, and in the functional domain and like core or something like that, if you have to, call the function like the physical name of the external entity. Like in this example, we've got a bank and end user and environment. Create an entity in your architecture called environment, even if it exists in the functional domain, that's fine. Because you're trying to get your functional inputs and outputs to and from this element, all right? So that's how you would do it in a tool like that. Also, the high-level mission descriptions, that tells the story. That lays out the functions for you in the sequence as the story is told. So it even says keywords like while. If you hear the word while, that means and. So you need to put an and in your functional flows, right? Or you'll see the word or in there. Or if it's not performing a mission, then it's in maintenance. Then it's performing maintenance, or it's ready for maintenance or something. So then you have perform mission as a function, and then allow for maintenance or whatever as a branch off of an or branch. Your use cases, your lower level use cases. So if you need to decompose higher level mission descriptions into lower and lower levels, the use cases are a great tool for that. Once again, use cases I run through in the Introduction to Systems Engineering course. So check that out. It's in module 5 for the pre-2018 version, and it's in module 4 in the more recent post-2018 summer 2018 version. And also existing designs. Ask yourself, if your system is replacing something else that performs better than that thing that it's replacing, ask how it's currently done, and understand in your mind that that's a starting point, and it's okay to fiddle with it if you need to in order to make your system perform better. But that's a good starting point. Start high and then work your way down. So top level mission phases, pre-mission, so your primary mission, perform whatever it is, and then decompose into sub phases, your pre-mission, your mission, and your post-mission phases. Wasson talks about that in part 1. Decompose those sub phases into lower levels if you need to. Go as deep as you need in order to capture the concept well enough for a developer to develop the system at acceptable levels of risk. That's how you know how far down you need to go, right? So ask yourself, when you're at a certain level in your functional hierarchy, do you think a design engineer can take over from here and design a system that does the things that are described by this sequence of events at acceptable levels of risk, right? And some areas will be high level while others go deep. For my own Capstone project, I did a automated gas pump, and basically the car pulls up to a gas pump. It's kind of like an ATM more than a gas pump. Pulls up to an ATM looking thing with a robot arm next to it, and they interface with the ATM part and tell it how much gas they want and whatever without getting out of their car. And then the robot arm does all the cool stuff that it refuels the car basically. I focused very, very little on the ATM part because that's very easy to engineer all that. And a design engineering team, a developer could very easily create that. So it's not worth diving deep into the architecture of much of that stuff to get it right. I focused instead on the robot arm part of it, right? A lot needed to be answered for that. There's a lot of high risk, a lot of immature technologies, a lot of moving parts, if you will, that needed to be solved. So that's where I focused most of my efforts. So my ATM portion only got, level 2-ish for in some areas. Didn't really go into level 3 in any of it. Whereas the robot arm piece, I went down to level 5 and 6 in some cases, depending on which apparatus was being worked on, right? Retain all of your input and output relationships. And in the lessons learned slide next, I'll show you what I'm talking about there. So all of the inputs and outputs, and really it kind of starts at the context diagrams. That's all your inputs and outputs, right? So you capture all your inputs going into your fuzzy cloud system. Your system does some magic and it provides outputs back out. And you've captured that in your architecture. And now you get to solve what it does on the inside and takes all those inputs and does some magic. I mean, you decide what the magic is that it needs to do in order to generate all of those outputs. If through doing all of that, you figure out that you need even more inputs or provide even more outputs, that's fine. Just add them to the architecture and update the context diagram or whatever as you need to. That's the purpose of all of this, is to make sure you get it right. So nothing's really written in stone, okay? So it's okay to update things as you go. Things that typically get left out of the functional domain are a lot of the ilities. For example, reliability. How do you model from a functional perspective reliability? You don't really, because a lot of reliability has to do with the physical makeup of systems. Some of it might have to do with things like redundancy and whatnot, but even then, that's still physical, right? So redundant subsystems would be a physical thing, right? So it's okay to leave some elements out of the physical domain, or the functional domain, I should say, right? Don't forget your EVM updates. So before you submit your functional analysis report, update your EVM information, and then also check the rubric before you submit as well. Common mistakes, got a couple pages of these. A lot of functions might be missing inputs or outputs. All functions have to have at least one input and one output. You might even be asked that at the very end of the presentation with either CJ or Dr. Flanagan. All of the functions have to have at least one input or output. Another common mistake is parent inputs are not flowed into the children. Children outputs are not flowed back up out into the parents. And this illustrates right here what I'm talking about. You might start with an external function in green here and have a parent function shown in blue here. And then your job is to decompose this into the children functions. The starting point is the boundary of this function. Let me see if I can zoom. Yeah, I can zoom in. So this black boundary, I should have made it white, but that's all right. The black boundary around this parent function is where things start. You know, before you reiterate, in fact, I'm going to end the presentation, and what I'm going to do is cut all of this, go back into presentation mode and make my point. The parent function is right here, and you see with your eyes that you've got, this might be a context diagram. External thing is providing energy to your system, to your main function. It's also providing data into it. All right, your job is to work the magic inside and produce another data element and some forces like pushback or a push-pull rod, or I don't know. How do you do that? Well, let me undo what I just did and then go back into presentation mode. You figure out what your system needs to do, but you keep those inputs going in and you hand them off to the children, right? So take this energy one and give it to child one. Data one can go to child one too, or also in this case, that could go to some other child and, you know, in a different case. But the point is, they're all accounted for, right? So these two inputs are accounted for. They go to a child. The child does its magic and it provides data, another data element to the second child here. This child does magic with that data. It takes that data and does some stuff, and it provides a signal as an output, and it goes into child three. Child three takes that signal, it does some magic, and it provides the second data element and the force as an output. Back to the parent. In the architecture that you're creating, you'll give it to the parent, and then the parent will again give that element to the external entity. Right? So make doubly sure that this relationship is kept. Don't let the child give it directly to the other parent from an architectural standpoint. Keep everything bound within the confines of the borders of your system, right? So the child gives it back to the parent, and then the parent says, okay, thank you, child, and gives it to the other, you know, the parent over here. I like to think of this kind of relationship as making like Thanksgiving dinner or something. You've got all the relatives that are from the outside of the house coming to the house, and the parents have to prepare for Thanksgiving and the children have to help with it. The parents get the groceries, right? Think of the groceries as one element, one big giant fat element, or the individual elements of groceries as inputs. Groceries are an input. There's other inputs also. You've got dishes, right? So you got to have somewhere to put all the Thanksgiving food. So dishes is another input, energy going into it, and the tools necessary. Those are all inputs that the parent gives the children. So the parent will lay out all the groceries, and they'll point out all of the different utensils that the children will use to make Thanksgiving dinner. And then they'll say, here's all the tools that you need. Here's all the groceries that you need. Now, Frank, I want you to make the turkey. Vanessa, I want you to make the stuffing. And Edward, I want you to make the pie, and on and on. How many ever children they have. They might have different responsibilities. Some of them depend on each other. Like you can't do the stuffing without, I don't know, if you're going to put the stuffing in the turkey, then you need the turkey. So child one needs to be done with the turkey before child two can put the stuffing in the turkey, etc. So that would be an output going back to the turkey. Think about it in your mind, how it would all work out. Although, at the very end of the day, the output out of it is each of the made Thanksgiving elements, like the made turkey, the made pie, the made stuffing, etc., are primary outputs, along with the dishes and the utensils and whatnot to use it all. Okay. So you got empty dishes going in, and you got filled dishes going back out to all of the relatives that showed up for Thanksgiving dinner, right? And that's the mission. The mission is to make the dinner. Another mission is to clean up after Thanksgiving, and it's a whole different story, right? So think of it that way. That's like the trick that I always use for that. Right, so hopefully that helps you. Another common mistake, poor hierarchy or no hierarchy, just like with the requirements. I just see functions all over the place, no parents or anything. They're just arbitrarily just functions all over the place talking to each other. That's very poor functional architecting, and you will not get a very good grade in your functional architecture if you do that. So it's got to be from the top down. Think about, like I showed you just now, it started as a plain blue box, if you will. And then in another iteration, I created the children inside of it, right? So top down is the way that we approach it. Another common mistake is missing key functions. What's your missions? What's your system's main mission? Its primary purpose. Some people forget this. They get lost in the weeds and they think about how they're going to receive data and do this and that, but they forget, what's the main thing? That should be the big box right here. What's its purpose? Make Thanksgiving dinner is one. Clean up after Thanksgiving is another one, etc. Another one is loosely bound, tightly coupled architecture. What this means is that it's a giant mess on the parent end. So the parent has like 10, 20, 30 different interfaces with the other parents, and they're just all over the place. The children are just giving information back and forth to all the other parents, the children within the other parents. And there's no real rhyme or reason to much of it. And that's what loosely bound, tightly coupled architectures are. By tightly coupled, you mean that the parents very heavily depend on all the other parents for their success. And if any of the children inside of any of the parents fails to do their job, then the whole system goes down and everything breaks. That's because everything's so tightly coupled with each other. A lot of functional interfaces among the different elements is what I'm talking about there. Also arbitrary functions, just making stuff up on the fly. It's not really based on anything, because that would be cool if it did things this way, right? It has to be based on something. Usually it's based on just thinking through a day in the life of the system. It's based on a description of the mission or the use case, right? It's got to be based on something. The functions are based on physical solutions. That happens sometimes, but it should mostly be top down, where we think about the functions should be based on the mission domain and the requirements domain primarily, right? Sometimes you might have physical solutions driving functions into the system, meaning the limitations of technology don't allow us to do functions that way, right? So the limitations of technology, we have to do them this way. And then you build the functions into the system that way. That's kind of more advanced, but you run into that sometimes, not a lot. The point is, you want to approach it from the top down. Your functions should be based on missions and on requirements and not on physical solutions. Another one is not using verb object syntax for functions. A lot of people, not a lot, some people will put a whole explanation or paragraph in the box that is their function. And don't do that. Just say what it is, a verb and an object. Make Thanksgiving dinner, right? clean up after, or clean up Thanksgiving dinner, or clean up dinner, do dishes, make turkey, right? Not decompose far enough, so you get a very high level functional domain. It's not, not excuse me, it's not very robust. Not that might be because your mission domain is not very robust, right? So it's got to be decomposed far enough to where, what's that point earlier, go as deep as you need to in order to capture the concept well enough for a developer to develop at acceptable risk, right? If it's not decomposed far enough and you could drive a truck through it and a developer could cheat their way out of anything, then it's not developed or it's not decomposed far enough. Also, decomposing COTS elements. If you're incorporating something off the shelf, I said it way up here in the proposal part of it, as the off limits thing is integration of COTS and federated elements. It's okay to have some COTS in there, just not all COTS, right? So you just go to the store and buy a bunch of toys off the shelf and take them apart and put them together in a different way or whatever. That's an example of that. Some COTS elements are fine, like aircraft, military aircraft have the same radio set for the most part, the ARC 210 radio set in a lot of military aircraft and vehicles. In fact, those are COTS elements. Don't touch the inside of those. You don't have privy over that, right? You can't do anything about the fact it's not COTS anymore if you're diving into it. So leave it alone. Your concern is with their interfaces, how it's talking to your system. What are the inputs and outputs to and from that COTS element, right? So leave it at its own level and don't go inside of it. Don't decompose its functions or anything like that. Just say what its primary functions are, what it offers your system, and then the inputs and outputs to and from the COTS elements, right? Hopefully you got a lot out of that functional analysis report section. Let's move on to the trade study, right? So where does the trade study fall? It's right here. So as one of the products of performing your concept design step right here, and concept definition, right? So it's same as the other courses, meaning refer to the other courses that you've taken that you've done trade studies in. You did one for your introduction to systems engineering course. You did one for your management, no, not your management projects one. You did one for your concept design one. You did another one for your system design and integration one. You might have done one for your T&E one. I can't remember, but at least you've done at least 3 trade studies, either individually. You did an individual one for your intro course, and you might have done group ones as group projects for those other 2 courses I mentioned. Use the same methods that you used for those. There's nothing special about the capstone for this. This is just proving to the university that you know how to do trade studies. There's 2 different ones that we teach you at Hopkins. One of them is the AHP, the analytical hierarchy process, which is in the intro course. And then there's the one with the utility curves, which is the one that's taught in the conceptual development and the system design and integration course. Use one or the other. You can't use really both of them because AHP uses, remember, the eigenvector math. That's to convert your subjective criteria into objective, basically bound requirements or bound parameters. And the utility curves does the same thing. It's just on a utility curve. Component alternative factors, things you want to think about when you select your different components. Choose something that's high risk, critical, and immature in your system. Choose something that's essential to the primary mission of the system, and choose something that's easy to obtain a lot of data on online. Don't make it more complex than it needs to be. Don't think that you need to call up a bunch of manufacturers and try and get their data sheets and things like that. It should be easily obtainable through simple web searches to get data sheets with enough information on it to perform analysis of the different alternatives, right? Remember, the point is to prove to the university that you know how to do a trade study. It's not to create a whole system architecture with like a valid, no kidding, trade study for an actual system. It's just to prove to the university that you know how to do a trade study. If you do cost is optional, but if you do cost, it should be independent and it should not be one of the criteria, right? So you factor cost after. Once again, don't forget EVM updates, and then once again, check the rubric. Common mistakes here, there's not enough that's worthy of 2 slides. So common mistakes I see are utility scales are inconsistent, meaning that one one of the factors or one of the criteria will be on a scale of 1 to 5, and one other one will be on a scale of 1 to 10, and another one is on 1 to 7. They've all got to be on exactly the same scale, otherwise you're skewing your results. Another one is that the criteria are not based on requirements. Make sure that they are definitely, for sure, based on requirements from your requirements analysis report or draft requirements that will go into your A-spec. All right, they have to be based on requirements, shall statements that you have in your spec, directly traceable to those MOPs. The other common mistake is that utility scales are not linked to thresholds and objectives. What I mean by that is, and if it were quick for me to draw this out, I would, but that's all right. If you think about the, let's say for the Y scale, envision in your mind the Y scale of a utility curve is just a scale of 1 to 5, just like I talked about. And the X scale, the X axis, is like speed. It's like top speed. If there's a requirement that the system shall go, or that the system shall have a top speed of 80 miles per hour threshold, 100 miles an hour objective, at the 0 point, or the lowest utility value, it should be the threshold, which is 80 miles per hour. That should be where everything begins. And the end, the maximum value is 80, or as 100. That's the objective. So the scale goes from 80 to 100, right? From the bottom to the top. And you fill in the entire thing. The entire graph is filled in because there's value there. That's what utility values are. There's the least value is at the threshold and the most value is at the objective. Right? How that shape is curved is up to you. Usually that's driven by the users or user representatives, but you can do it for this project if you're using utility curves. It's a different story with analytical hierarchy. In that case, it's just a simple table because there's numbers involved. You don't even need to use the eigenvector math for that, right? Another common mistake is if you use AHP, then the math is sometimes incorrect. And the way that I always check, it takes a simple glance to see that it's wrong. And if you remember taking your intro course with me and I caught it, the trick of the trade, now that you're here in the capstone, is, and I'm going to show you in a second here. I think it's module 6. Homework 6. Here we go. Recall this template and take a look at the squared matrix. Remember this? So look at the squared matrix. This is where your eigenvector math is done. Look at the gray boxes. It says 5 in all the gray boxes. That's because you've got 5 elements that you're evaluating. See how there's 5 rows, 1, 2, 3, 4, 5. And you've got, since there's 5 rows, automatically there's 5 columns, 1, 2, 3, 4, 5 columns. Right? It's a 5 by 5 matrix. That means the middle diagonal, because of the way eigenvector math works, the middle diagonal will always equal the amount of options that there are, which is 5. And if you mess it up, if you mess up the math, let me go in here to any one of these and just erase something off the end here. And we do Control X here, hit enter. It didn't do it. Let me try. It didn't do it there either. Might need to be done over here on this end. So let's try 2.5 right here. There it goes. Yeah, so it's on this table over here. So these things aren't evaluating, the reciprocal values are not provided correctly. In this case, I put 2.5, the same value here, and it messed everything up. It messed only 2 of the elements up, but it messed up the eigenvector math over here. Now, instead of saying 5, it says 10.25. And I don't even need to check the rest of the numbers that it impacted because I could see immediately that the diagonal does not equal 5 all the way across. So that means there's something wrong with what you did over here in this table. And then the second thing I would do is go in here and look to see that mistake, to see that reciprocal is not shown there, which is 1 over 2.5, right? So that's one of the mistakes that I see on there if the AHP is used, right? That's the trade study. Let's go to the concept design report next. Here it is in the overall life cycle. It's also just like the trade study, an output of physical definition. during concept definition. Start in the functional domain, allocate top-level functions to subsystems. Ask yourself in your mind, what kind of physical thing could do this job? And then usually the name of the subsystem is the function. Think about it. Coffee maker. Coffee maker makes coffee. The function is make coffee. The component that does that is coffee maker. Interesting. Washing machine, I don't know, dryer, clothes dryer, if you want to put the full name on it. I don't know, computer, that's kind of a nerdy one, but I don't know, you could think of a bunch of other ones. Blender, right? Food blender, food processor. Usually the thing is named after the function that it performs. So that's really kind of an easy way to go about it. Oops. Here we are. All right. And I accidentally made this bigger than it needs to be here. So, all right, start at the top and work your way inward, meaning don't dive into the little components all the way down at the bottom. Start at the top of the functional domain and allocate the top functions at level 2 or 1 or whatever to subsystems. And then go to each of the children inside of each of the functions. Think about in your mind that they are a part of this subsystem, and imagine in your mind if these little children, which components perform the functions that the children perform, right? One of the other things too is, yeah, and I'll mention it on the other slide. Make appropriate connections, the physical connections, based on the functional inputs and outputs. So the functional inputs and outputs, let me go back to that slide here. These arrows are the functional inputs and outputs. Now the question is, what transfers the energy? What transfers the data? What transfers the data? What transfers the force? That's the physical interface. Energy is probably transferred by a power cable. Data is transferred by a data cable like Ethernet or the phone line. Same there. Forces can be transferred by all kinds of stuff. Hard mounts, vibration mounts, push-pull rods, etc. Sorry, got a text probably from, all right. Let's continue on. Allocate functional inputs and outputs to physical interfaces. I just talked about that in your tool. And that in core, they use the transfers and transfers by relationship for that. So you'll go to the item and then you'll double click transfers or transferred by, and then it'll come up with links, and you have to connect the links. And the appropriate connections right here are called links in core. If you discover you're missing obvious elements after functional allocation, go back and update functions and then allocate as normal. So if you ask yourself, I know this thing should have a display in it, but what's driving a display? I went to my functional domain and there's nothing driving a display into my system. Well, then you just go into your functional domain and you kind of have to trace your way all the way back to the requirements domain usually, because your functions can't just be arbitrary, remember? So if you discover that you don't have a display and you meant for there to be one, like it's intuitively obvious that you need to have a display, a means to communicate to the user, add the display and work your way backwards into the functional domain. Add a function to inform the user, for example. That would be the function for that the display carries out. And then what's driving the inform user part is probably a requirement that says it needs to interface with the user, right? So if you don't have a requirement like that, then make one up. And now you just got one new requirement from that. Don't forget about software also. Some students forget completely about software, and it's all hardware, the whole system, but don't forget about software. You don't need to get too deep into software. Just the software elements themselves, like either the operating system or the applications on the operating system, if you have it that way. One thing that's commonly asked at the end is if the software is distributed or centralized, right? So an aircraft has distributed software in it. Each of the little black boxes throughout an aircraft, each one has its own internal software that's running on it. Your laptop is centralized, so it's got Windows or Mac operating system and a bunch of applications running with it. It's all centralized in one machine, right? So that's an example of centralized. A vehicle has, believe it or not, a car has distributed software. It's got the ECU is the most common element that's got the most software on it, but your radio has independent software. The dashboard has independent software, etc. Your navigation system has different software, etc. Don't forget about EVM updates. Check the rubric once again. Common mistakes for the concept design report. Once again, poor hierarchy or no hierarchy. Missing key components, the main mission purpose, just like the functional domain. Arbitrary components are not driven by functions. You just willy-nilly put some functions in there or some components in there just because. Don't do that. Also, a key here is one-to-many functional allocation. What do I mean by this? When you allocate functions, you have to do it in a top-down fashion. You start at the function and you ask yourself which component can perform this function. And then you allocate it, you assign it to that function or that component in the physical domain. Something that you should never do is ask yourself which components, plural, can do this function, right? It's always one component that does the function, right? So one function should not ever be allocated to more than one component is the point. And sometimes you'll see that. Don't do that. That's gold plating the system. And that could have really serious impacts. If you do this in the real world, think about like a function to communicate with the user or display something to the user. If you allocate that to multiple displays or to each subsystem, I should say, now each subsystem developer, if they're independently contracted, has to put a display into each of their subsystems to try and fulfill that function, right? Which is probably not your intent. Software is nowhere to be found is another common mistake. Off-the-shelf elements are decomposed. Once again, stay out of the box, right? That's not your business. What goes on inside there, what it's made out of inside of it. Just leave those alone. Focus only on their interfaces, right? So those are the common mistakes for the concept design report. Let's go to the A spec. The A spec is the primary output out of all of this, right? This is the big mother of all of the deliverables that you have for your capstone project. Its purpose is to add to some notional request for proposal in a subsequent development contract to go off and develop your widget. If you've been using model-based systems engineering tool, this will be by far the easiest report to generate because it's just a matter of generating the report and maybe dressing it up according to the template that you've been using. You want to update the requirements with any new information that you've gained from the trade study and the functional analysis and the concept design report, etc. Add new lower order requirements for the subsystems and components as needed if you need them. Ask yourself, do I feel comfortable placing a contractor on contract to develop a widget as described by these requirements? If you don't, then you probably need to do a little bit more work. If you do, then press forward. Don't get too detailed. Here you want to allow the design engineer some what's called trade space. You want to give the design engineer flexibility to exercise their trade. You should still focus on performance. We should not be putting specific solutions into the system. You can have subsystems called out and you can even have components called out. Usually they're named by the function that they're performing, right? However, don't put specific solutions like, I don't know, I'm looking at an HP Envy. Don't put an HP Envy as your requirements in there because the design engineer can figure out all that stuff. Don't put the exact dimensions of the display, etc. Right? So the design engineers figure that stuff out. Quantify as many requirements as possible. So you want to say how well these things should be performing or how fast or how reliably. Those are the three common things that the requirements should describe, right? Once again, check the rubric. I can't emphasize enough the requirements need to be quantified and AKA testable, right? Common mistakes, low number of quantified requirements, less than 75%. More than 75% of your requirements should be measurable / testable. Might not be detailed enough, too abstract. You can drive a truck through your requirements. The thing that I like to do is play devil's advocate. And you cheat yourself out of any requirements and then close any gaps as needed. What I mean by that is, put your evil developer hat on and think about I'm going to steal so much money from these guys. They have no idea. They're not going to get the product that they asked for, but it will certainly meet the specification, right? So think about things that way. And sometimes they're also another common mistake is you're stepping on their toes. Use whatever analogy you want. You're not a design engineer here. You're a systems engineer. You're a systems architect. You're not the design engineer. Either you never were one or you are one no longer, right? So you want to hook them up. You want to give them the information that they need to design the widget for you using their expertise, so that it meets those requirements. And also, common mistake is that the requirements in the A-spec are largely unchanged from the requirement set that's in the RAR. Like, you haven't grown much of your requirements, you haven't changed very much of them or refined them. In which case, why did you do the whole project? You know, all the stuff that we've talked about up to this point between the requirements analysis report and the A-spec, why'd you do any of it if nothing really changed, right? So we've got to see some amount of growth here. Usually the biggest growth is the number of quantified requirements, because your MOEs up here in your requirements analysis report, these MOEs, just like this says right here, sometimes they're subjective. And as you go through all of this process, you quantify those as lower level performance requirements, right? Test report, choose a critical element for primary mission. Don't get too detailed with it. The purpose of this test report is to plan for actual arbitrary test events. And here your main aim here is cost, schedule, and resource estimates. You don't have to do the estimates, but you're hooking up the people that will be doing the estimates by providing them. It's not a test report, by the way, it's a test plan report for the project, which is a little confusing, but it's a test plan, but it's a report for the Capstone project. Common mistakes here. Usually this one I have almost no comments on for most of my students. They get it right the first time. Choosing the entire system is a mistake. Choose a component or some element within it. You know, if you choose the entire system, you're going to have a 100+ page document, which is crazy huge. So just do it to get the point across, which is that you know how to develop a test plan. Unfeasible test methods also chosen. Too expensive for what the system is. What do I mean by that? Think truly. This is really a big part of being a systems engineer, is being able to see the forest through the trees. And if you've got all these test methods that are being called out, think about how big this is going to be, how much money it's going to cost, how many people it's going to take. And if your little wimpy little UAV program, you know, they're not going to get very much money. They're certainly not going to get enough money to have a whole wind tunnel facility built and all this other stuff that you're begging for through your test methods. So understand really where your system fits in the big picture as far as cost, schedule, resource availability, and pick the appropriate test methods to reflect that, right? So a lot of people, you know, their eyes get bigger than their wallets, if you will, when it comes to choosing test methods. Understand the greater context of things here. Risk report, begin identifying, assessing in the proposal, and run through each of the, update your risks as you go through. At the back end of each of these reports I've been going through, you have to update your risks. Work some mitigations into the architectural design itself. Use the same philosophy as taught in the classes. If updated with each deliverable, the risk report should be very, very easy. Then it's just a matter of, what you've done between the last report and now, which is usually nothing. And then check the rubric once again. Common mistakes in the risk report: no new risks as the project progresses. Excuse me. So you don't have any new risks. So once you submit your risks in the proposal, if you don't do anything with them, or if you don't come up with any new risks, then that's not good. Mitigation steps don't lower the risk at all, but it says that they lower the risk. For example, when you have a step to plan, or if you have a step to assess something or study something, those don't lower risk at all. All those do is shed more light on the current risk level. So think about the greater context, the greater picture of it. Did it really reduce the chances of the bad thing happening? If the bad thing happens, does planning really reduce the consequences of it? Probably not. It didn't even get you to the, fixing it or assessing or coming up with requirements. None of those things reduces the likelihood or the consequence of risk. All those do is either get you ready for the next step or shed more light on the current risk level, but that doesn't mean don't include them, because you might need them in order to do the next step, which would reduce the risk, right? So just keep that in mind. Maybe the risk level will stay the same for this step, and then the next step will lower it because you did step one, right? So keep that in mind. It's kind of like a little mini project, if you will. Mitigation steps: lower incorrect category. If it prevents the bad, this is the rule of thumb. If it prevents the bad thing from happening in the first place, then it lowers the likelihood. Like driving for a flat tire risk, if you drive carefully, there's less of a chance that you'll get a flat tire. If you have good tires on the car, there's less of a chance you'll get a flat tire. If the bad thing does happen, if you do get a flat tire, for instance, and the mitigation step lessens the harm caused, then it will lower the consequence. So if you do get a flat tire, having a spare tire in the trunk or having roadside assistance, those are things that reduce the harm or the badness that's caused by having a flat tire. Make sure you focus on those. Like a lot of my students make these mistakes that are shown right here on this slide, right? So check this out. Make sure that you do these when you submit that. Final report and oral presentation, it's the smallest deliverable. The final report is typically less than 15 pages to include the cover page and whatnot. Use the lessons learned to your advantage, meaning if you forgot to do a lot of stuff in your project, talk about it in lessons learned. Like you neglected an area of the architecture, like tight binding and loose coupling. It takes a lot of work to break out of a wiry mess like tight binding and loose coupling. It takes a lot of work, a lot of labor hours to break out of that. But use lessons, if you don't have the time to do that, use lessons learned to talk about. If I had more time on this project or more resources, I would have gone through the functional domain and arranged the functions so that the amount of interfaces between the parent functions would have been minimized. But I didn't have the time, but I would have done it. So as long as the key is, do you understand the philosophy behind it? That's really what we're after. Once again, to get to the main theme or the main purpose of the project, it's to prove to the university that you have the subject matter mastered, and the lessons learned is one way to help prove that, right? The presentation itself, the slides will act as cues for discussion. In other words, don't put all of your different diagrams and artifacts on slides and just go through each one at a time. So don't paste each diagram onto the slides. Use one or two diagrams from each domain as talking points. In the background, either CJ or Dave Flanagan and myself will be looking at your actual artifacts, your actual reports, and coming up with questions and stuff from that. Look at past student presentations on the 800 site just to gauge and understand kind of the scope for the oral presentation. And once again, check the rubric for that. Before I leave this entire subject, I know we've been going on for a while now. I don't have a timer here, but we've been going for a while now. Before I leave, I want you to walk away with some more frequently asked questions that aren't necessarily related to each of the other artifacts. These are things that I usually see asked from CJ or from Dr. Flanagan to students. Be able to address the following. Define a KPP to a layperson and why KPPs are important to the development of a system. Explain and defend why you chose the KPPs that you did. Explain why using thresholds and objectives and requirements are important. Explain how many explain how many inputs and outputs are required for each function. Some students don't do that or don't, the common mistakes in the functional one that I showed, one of the points was that you're missing inputs or outputs. So now you have to explain how many inputs or outputs should each function have, and the answer is at least one, right? Address that functions use the verb noun syntax. If they see that there's a big sentence or a paragraph written on the function, then you're doing it wrong. The logic flow for your functional domain, so be able to explain that. Explain where your software is within your architecture and be able to quickly find it. Students usually use color coding. You can color code software a different color. Why you chose specific trade study utility curve shapes if they're different than linear. Sometimes they're different than linear, which is fine, but be able to defend that. And then trace your trade study criteria to the requirements. Obviously there's going to be more questions than this, but these are the big hitters. Usually KPPs are very critical, important. So that's really all there is to it. As far as my tips and pointers and things like that, as long as you stick to the rubric, as long as you stick to the guidelines, and as long as you incorporate my feedback, then you'll probably do very well on the Capstone project. Another big piece I would highly encourage is to really stick with it. I'm not going to track your progress. I have 30 plus students every semester that go through the Capstone project, and I don't have time to, for lack of a better term, babysit all of my different students and figure out that you're a month behind what you said you were going to be on your requirements report. I don't have the resources, I don't have the bandwidth to track all your, if you're late or not. I had students, that just kind of disappear into the void, and I just never hear from them again, and they don't get their master's in systems engineering. I haven't heard from them for 5 years. In some cases, I'm not going to write you an email and ask what the status of your project is. I simply don't have the bandwidth for that. So, you're a working adult. This is a master's degree. It's not an undergrad. It's not high school or elementary school. It's on you as a grown adult to track your own progress and to work your way through the project. A word of encouragement is that, this is a limited thing. This is a limited part of your life. This is only, 6-month span or 10-month span or whatever it happens to be of your life. But the master's degree lasts your entire life, right? Think of it that way. You're 30-something-year-old person now, late 20s, 30, early 30s something person now. 10 of those months are spent in not necessarily hell, but it's not fun, right? Doing all this stuff. But then you get another, hopefully, 70 plus years of payback for those 10 months that you dedicated to this project, right? So there is an endpoint. It is bound by time. There's a start point and there's an endpoint. Don't be one of those ones that never has an endpoint. Get through the project, get through it by the time period that you say you're going to get through it, because there's a half letter grade deduction for every semester that you don't get through it. So keep that in mind as well. And good luck on the project. Let me know if you have any questions. I'm going to go ahead and stop the recording. I think I've talked long enough. And hopefully you found this useful and valuable. So with that, have a great day, and we'll talk to you later.